Good morning, everybody. So we are starting with chapter number 1, the crystalline state. So you know that whenever a gas or a liquid solidifies or freezes, when you're talking, these are the two terms that you normally use, solidify or freeze. So whenever a gas solidifies or freezes, or when a liquid freezes, then what you get, the solid that you get can be of two types. One could be a crystalline material where the atoms are all ordered. Okay, and such a material is called a crystalline material. So you can actually, imagine, let's say we are talking of a metal like copper. So every atom of copper is sitting at designated positions. So there is a repeating nature of the arrangement. So then we say it is crystalline. And if I know how the arrangement has happened for the first few copper atoms, then I can predict how it's going to be in all the three dimensions. Then the second type of solids that you can get may be amorphous materials or disordered state. As the name itself suggests, it's completely a disordered system. There is no order in which the atoms are placed, atoms or molecules are placed. There's no designated locations. Then you say that the material is amorphous. In this chapter, we are going to be mainly discussing crystalline materials. So first of all, let's talk about what is a crystalline structure. How do you define a crystalline structure? It's a three-dimensional arrangement. It's a three-dimensional, regular and infinite array of atoms or groups of atoms extending over the entire volume of the crystal. Let's say I have a crystal and I am going to actually talk about how the atoms or groups of atoms are arranged. So first of all, it's a three-dimensional structure and it's an infinite array. We say infinite array simply because the interatomic distances are very small when compared to the real size of a crystal. So infinitely large number of atoms or groups of atoms have to come together, get placed in their designated locations, and then you get the crystalline structure. So when we talk of crystal structure, there are two words that you should know. One is called the lattice and the other is called the basis. Okay, let's see what is a lattice. A lattice talks about the geometry of the arrangement. A lattice is an infinite periodic array of points. It's just geometric points in space. Okay, and where are these points put? The points are put in locations where the atoms or groups of atoms should be placed. And what is a characteristic of a lattice? So if you take any point in the lattice, then that point will see around it an identical environment as seen from another point. Okay, so if I take a lattice point and then try to look at what that lattice point is going to see around it, like for example here I'm taking a lattice point, around it it is able to see 4 lattice points. Now if I take any other lattice point, that lattice point also should show an identical environment. So this is one of the. Now let's move to what is a basis. So what is sitting at these points? At each of the lattice point is called the basis. And what can be the basis? The basis could be just a single atom. Like for example, if I'm talking of, let's say, copper. So copper, it's a single atom sitting at its position. Or if I'm talking of polonium, okay, a single atom sits at a lattice position. And then in some cases, it could be actually a collection of atoms sitting at a position. We'll see examples of those as we go along. And we call an atom or a group of atom as a basis if each lattice point that is being occupied by the basis are identical in terms of composition, relative orientation and separation. That is, if I take a lattice point, on the lattice point sits this basis, and every basis sitting in that lattice should be identical in terms of composition, identical in terms of orientation, identical in terms of structure, identical in terms of separation between atoms if I'm talking of more than one atom sitting at a lattice. And how many atoms can be there in a basis? It can be as low as 1. I gave you the example of polonium, or it can be as large as thousands. Where do you see thousands of atoms sitting at a lattice? For example, in a protein structure is a very large molecule comprising of thousands of molecules. So each lattice point would be occupied by thousands of atoms. And so now what is a crystal? A lattice plus the basis gives you the crystal. The lattice arrangement talks about the geometry, and the basis in combination with the lattice gives you what is the crystal. It talks about the composition, it also talks about the arrangement, the geometry. Now let's move along and talk about what is a unit cell. So just now we talked about a crystal as a lattice per basis. It's also possible for us to talk about a crystal in terms of what's called a unit cell. So what's a unit cell? A unit cell is an elementary building block, or the smallest block consisting of atoms or group of atoms, which when moved along its edges along 3 dimensions can generate the entire volume of the crystal. Okay, what I mean is, I'm talking of 3 directions. Okay, here I'm showing 3 directions. And let's say I'm talking about a group of atoms sitting at a lattice. Now, how do I generate the entire crystal? If I move this group of atoms along in steps along these 3 directions, then what I would be doing is I would be able to generate this entire crystal. Now, this elementary unit, which when moved along these 3 directions generates the entire crystal, is called the unit cell. It's the smallest building block. Okay, it's the smallest building block. May have more than one atom sometimes, may have group of atoms. There may be a situation where at all these 8 corners one atoms are sitting. Okay, whatever it is. So this is the smallest unit, which when moved along 3 directions gives you the entire crystal. You can generate the crystal by just moving the unit cell. It's an elementary building block, or the smallest block. A and B are not collinear, but then they are not perpendicular either. So when you are talking about a 3-dimensional lattice, we need to talk about 3 such parameters: A, B and C. They are called the cell parameters, or they are also called the primitive translation vectors. By translating these lattice points, take one lattice point, translate along the x-axis in steps of A, translate along y-axis in B direction in steps of B, translate along C in steps of C. Then what you generate is this entire lattice. Okay, and how should the points be arranged? They should be arranged in such a way that if I take a lattice point R prime, the lattice R prime, you should be able to reach from a lattice point R by translating through a vector T. That is, from a lattice point, let's say this is my lattice point R, I should go to lattice point R prime by translating through a vector T. This is called the translation vector T. And this translation vector is actually made up of A, B and C. You go through n1 steps along A, then n2 steps along B, n3 steps along C, then you reach the point R prime. And this n1, n2, n3 are integers, and T is called the translation vector. Please, this is called the translation vector, but A, B, C are called the primitive translation vectors. Okay, now look at this picture here. we have a set of lattices, and we are also showing you some atoms are sitting there. Now you are shown a translation vector A1, a translation vector A2, then on this side you have a translation vector B1, there's a translation vector B2. Which of these are primitive translation vectors? Let us see. You're going to see here that by moving through a step A1, you are not able to reach an identical atom location. You're not able to move and reach an identical atomic location. But by moving through a distance A2, you are able to reach an identical location. Similarly, on this direction, if I move through B1, I'm not able to reach an identical location. But by moving distance B2, I'm able to reach an identical location. So which means these points, this point, this point, this point, these are all not bases. These are not lattice points. This point is not a lattice point. This is not a lattice point. Okay. So what are these? This entire thing constitutes a basis. This entire thing constitutes a basis. This constitutes a basis. This is a basis. Similarly here, if I extend, there is a basis here. This will be the basis. Similarly here, there is a basis. Now look at this. If you treat each of these green identities as a basis, a combination of two atoms. Now look at this. To go from this to this, you need to move through a distance A2. Similarly, from here to an identical location you want to move, you have to move through a distance B2. Okay, similarly, this guy, if he has to move through a distance A2, he reaches here. So that's the symmetry you're seeing. So therefore, A2 and B2 are the primitive translation vectors, not A1 and B1. So let's again define what is a primitive translation vector. Primitive translation vectors are the three adjacent axes of a primitive cell. The volume, the unit cell enclosed by this primitive A, B, C is called the primitive cell. Look at this. I have my primitive A, B and C. So the volume enclosed by this is called the primitive cell, and these sides, this is a unit cell, and these A, B, C are called the primitive unit vectors or the primitive translation vectors, and this is the primitive cell. And the direction given by A, the direction given by B and the direction specified by C, these three may be orthogonal, may be non-orthogonal. These three non-collinear directions set by A, B and C vectors are called the crystallographic axis. The crystallographic axis essentially tells you the geometric symmetry of the given crystal. Now let's give another definition for a primitive cell. A primitive unit cell is a minimum volume cell. It's a minimum volume cell defined by the primitive translation vectors ABC. And if you try to look at how many lattice points are going to be associated with it, you will find that there will be only one lattice point per unit cell. Look at this. In this picture, for example, you are seeing 8 lattice points sitting at all the 8 corners are there. Then you will say, is it 8? Sorry, it's not 8. You must remember that this one lattice point is shared by 8 cells. 8 cells. Okay, you can imagine 4 on one plane, 4 on the plane below, and it's shared by 8 cells. So is the case with each of these 8. Okay, so 1 by 8 is the contribution to this unit cell by this lattice point. Okay, therefore 8 into 1 by 8 gives you 1. So there is only one total lattice, or there will be only just one basis for this particular primitive cell, unit cell. What is the volume of the cell? The volume of the cell, these are after all vectors, the volume of the cell will be Vc equal to A dot B cross C. But sometimes what happens is, we may not always consider only cells, primitive unit cells in our discussion. Sometimes it becomes easier for us to deal with unit cells which are larger, though not primitive. Okay, but what is the use of that kind of a larger cell? You may select the larger unit cell, which is non-primitive, because that exhibits the symmetry of the lattice more clearly. So such a cell is called a conventional cell or a non-primitive cell. Now look at this picture. Here I have a cubic cell. The distance between each of these sides is A. This is cubic. This is primitive. Each corner contributing 1 by 8. So 8 into 1 by 8 is 1. Now look at this. This cell is a non-primitive. It's a conventional cell which we can call as a BCC conventional cell. Look at the side is A, and look at the lattice points. There is a complete lattice sitting inside at the body center, and then 1 by 8, 1 by 8 sitting at each of the 8 corners. So if I see what is going to be the total number of lattices for this cell, it is 8 into 1 by 8 plus 1, which is 2. 2 lattices associated with the with this conventional non-primitive cell. But sometimes it is easier for us to operate with this structure because this straight away shows that it is a BCC structure. So if I am more interested in the symmetry of the lattice, I could discuss in terms of a conventional non-primitive cell. Okay, now the basis associated with the primitive cell is called the primitive basis, and the primitive basis will have the lowest number of atoms as compared to other cells of the same crystal. See, so I told you we can define cells in more than one way. Okay, so when we are talking about a cell which is a conventional cell or a non-primitive cell, the basis that you may be associating may be not the same as in the case of a primitive basis sitting at a lattice point in a primitive cell. So what's the difference between a normal basis and a primitive basis? The primitive basis is going to be a basis associated with the primitive cell, and it will have the lowest number of atoms. And there can be more than one choice of primitive cell with equal cell volume for a given crystal. It's just a matter of convenience what we take. Like for example, you see here, I have lattice points. Okay, you can see all the lattice points. Here is A1, B1 orthogonal. Look at the area. This is a two-dimensional structure. The area is A. Okay, so that is A1 into B1 is the area. Now look at this. Here we have defined A2, which is same as A1, but then our B1 is not the same as B2. Now if you take this unit cell and try to find out the area, you will find that by translating this along this direction and this direction, you can get the entire crystal. And look at the volume of it. You will find that height into base. So the volume is same as this. Okay, but come here. Look at this. A3 same as A1 and A2, but look at B3 here. Now if you try to see what is going to be the area of this, okay, the area of this, you're going to see that, I'm sorry, there's a small mistake here. There's a small mistake here. You're seeing that this will also have the same area. This will also have the same area as A1 and as A1 B1 and A2 B2. So this also you can qualify as your primitive cell. Okay, now come here. Here we have written A4 and B4. Now if you look at this, this is not a primitive cell. This won't have the same area as these 1, 2, 3. This 1, 2, 3 are going to have the same area. Okay, so what we have this, the cell defined by A4 and B4, it's a conventional cell, all right, but it is not a primitive cell. But then the other three are all primitive cells, but different So it's a matter of convenience how we choose a primitive cell.